Hi everyone, this is Miss Moore and today we are continuing with Lesson 5, Roller Coasters and Pendulums. These are the most challenging conservation of energy problems at the grade 10 level. So hang on, this is going to be an intense lesson. If you don't have a copy of the lesson notes in front of you today, you can make your own notes on important concepts and example questions using lined paper. You will definitely need a calculator for today's lesson. So if you don't have what you need, please quickly pause the video and grab it before we continue. Today we're warming up with a classic conservation of energy question, the kind of question we should feel very comfortable solving at this point. A volleyball is hit vertically downward from the peak of its flight 2.8 meters above the court. If the initial speed of the ball is 9.5 meters per second, how fast is the ball going right before it hits the ground? Assume that mechanical energy is conserved, as we always do in Physics 10. Please pause the video here while you try this question. Just in case you're stuck, I'm going to give you a quick hint. If the volleyball is hit vertically downwards, that means it has an initial speed. This is different from being dropped. So V initial is not 0. It's 9.5 meters per second. As usual, we start with a diagram and a list of things that we know based on the information in the question. In this case, we're looking for V final, the final speed of the volleyball right before it hits the ground. Then we write out our conservation of energy formula. EK plus EP initial equals EK plus EP final. Right before the volleyball hits the ground, there's basically no space left between the ball and the ground. So H would be 0, which means that EP final would be 0. That means we're working with an equation that has 3 different terms in it, which leads it to be a little more complicated. We can isolate V final by performing some algebra. We can multiply each side of the equation by 2, we can divide every term by m, we can take the square root of both sides of the equation, and then substitute our values to find that the final speed is 12 meters per second. We're at the point now in the unit where these kinds of problems should be really straightforward and we shouldn't be getting stuck on the algebra. So if you're struggling with any part of this question, please come by extra help so we can work on this together and develop some confidence. Okay, on to roller coasters and pendulums. As we all know, the law of conservation of energy tells us that energy can be neither created nor destroyed. In Physics 10, we ignore all energy losses due to friction, which brings us to this fabulous formula we've been using so far. EK plus EP initial equals EK plus EP final. Roller coasters are an excellent application of the law of conservation of energy. This is how they work, and this is how they are designed. Essentially, they are a train powered by gravity. Usually the highest point on the roller coaster is the first hill that it goes up, if it's a traditional roller coaster. So you have this initial store of gravitational potential energy, or GPE, that is gained as you go up this huge hill, and then it's released dramatically throughout the ride as your speed increases and decreases. This first hill is so important in traditional roller coaster design that it has a special name. It's called the lift hill. If you've ever ridden the wooden roller coaster at Playland, this is exactly the technology that it uses in its design. The lift hill is the highest point of the ride, and so as the roller coaster plunges down the first drop, all of the gravitational potential energy that it had is converted into kinetic energy, or KE. Later, throughout the track, some of this kinetic energy is converted back into gravitational potential energy as the roller coaster gains height above the ground, climbing the next hill and starting to slow down. Over the course of the ride, the roller coaster's total mechanical energy, which we know to be the total kinetic plus the total potential energy, decreases. How could this be, you may ask? We know that energy is not created or destroyed. That's what the law of conservation of energy tells us. So how is it possible that the roller coaster's total mechanical energy is decreasing from the minute it leaves the lift hill until the end of the track? This is because of the friction between the roller coaster and the track, and the roller coaster and the air, which is called drag or air resistance. All of this friction causes a whole bunch of the roller coaster's energy to be converted into heat energy or thermal energy. By the end of the ride, all of the gravitational potential energy that the roller coaster had on the lift hill is lost. If there's any left over, the roller coaster deals with this by braking. Okay, let's do an example together. Let's assume that the roller coaster in this diagram is frictionless. What gravitational potential energy does the roller coaster have at point A, which is right here at the top of the lift hill? Let's summarize what we know. The mass of the roller coaster is 4,500 kilograms. Gravitational acceleration is 9.81 meters per second squared on Earth. How high is the roller coaster at point A? It's 12.0 meters above the ground. Now in roller coaster problems, we typically deal with a couple of different points along the track where the track is different heights above the ground. So a handy tip for roller coaster questions is to always use the subscript that specifies which height you're talking about. In this case, we're looking at the height of the lift hill or the height at point A. Okay, let's use our gravitational potential energy formula. EP equals mgh. Let's substitute in our numbers. $529,740 joules. That's a lot of energy, but these are real life numbers. And so typically we could convert that into kilojoules by dividing by 1,000, but we'll leave unit conversions for Physics 11. Now it's your turn. Please try part B. What gravitational potential energy does the roller coaster have at point B? Please pause the video here while you try this question. At point B, the roller coaster has 88,290 joules. Let's think about our answer for a minute. Is it reasonable? At point B, the roller coaster is much closer to the ground than it was at point A, so it should have far less gravitational potential energy. If we compare roughly 88,000 to 530,000 joules, it definitely does. Okay, this has been pretty simple so far, so let's make it harder. Assuming that mechanical energy is conserved, what is the kinetic energy of the roller coaster at point B to the nearest joule? To solve this question, we're going to need to use the conservation of energy formula. Let's work through this example together, and then you can try part D on your own. Initial kinetic plus potential energy equals final kinetic plus potential energy. But what is initial and what is final? We're used to problems where things are dropped or thrown. So how do we figure out initial and final for a roller coaster question? You can use any points on the track for which you have data. On this track, we have data for point A, B, and C in terms of height, but the only point that we know the speed of is point A because we know that the roller coaster is stationary before it goes down the lift hill. So we're going to use point A and B for our comparison in this case. I'm going to erase I for initial and F for final and replace it with A and B. Which of these quantities are zero? At the beginning of the lift hill, before the roller coaster is released, it's not moving, so the kinetic energy is zero. At point B, the roller coaster is moving and it is still above the ground, so we cannot cross off either of these quantities. Now, what are we looking for? The kinetic energy of the roller coaster at point B. So that's this quantity here, which means that when we replace each of these quantities with their formulae, we're not going to replace that one because we're actually looking for it. EPA is m times g times the height at point A. and EPB is m times g times the height at point B. We need to find the kinetic energy at point B, which means that what I've highlighted in pink is the variable that needs to be isolated. How do we get EKB by itself? We have to figure out how to undo the fact that MGHB is added to it. And the way we do that is we subtract MGHB from either side. How does this work, you may ask? Well, it's the same as if we had something like this from math class. 4 equals x plus 2. How do we get x by itself? We subtract 2 from each side. At the end of the day, m times g times hb is just going to be a number, so we're subtracting that number from each side. Now we have mgha minus mghb equals EKB. There's one more optional step you can do before you substitute known values, and that is recognizing that each of these terms contains m and g. So this can be factored out to the front of the expression. It's not going to change your answer, but it does result in a little bit less writing when you put your numbers in. Okay, let's substitute known values. EKB equals mass, 4,500 kilograms times gravity, 9.81 meters per second, times HA minus HB, 12 meters minus 2 meters. So EKB equals 441,450 joules. Okay, it's your turn to try one. Part D, assuming that mechanical energy is conserved, what is the speed of the roller coaster at point C? Assuming that at point A, the roller coaster is stationary. Just like before, you have a choice of where your initial and where your final position are going to be on the track. Because we've just solved for a bunch of information for point B, we now know more about point B than we did before, but the best practice in physics is to never use information that you generated yourself when you're solving a multi-step problem, just in case we made a mistake in this calculation. So my recommendation is to compare points A and C. Please pause the video here while you do it. Okay, so at point C, the roller coaster is going 12.5 meters per second. This question used the same algebraic steps that the previous question did, and the only difference is that the previous question asked for kinetic energy and this question asks for the speed. So when you're solving an equation like this, which can get kind of intense with all the variables, a strategy that can be helpful is highlighting what you're looking for, in this case VC, so that you kind of keep your eye on the prize as you work through all of the steps of algebraic simplification. Okay, on to pendulums. These also operate using the law of conservation of energy. A pendulum is basically a mass on the end of a string that swings back and forth and transfers mechanical energy just the same way that a roller coaster does. Examples of pendulums would be like Newton's cradle, which is that apparatus of metal balls where one swings and hits the others, and then the one on the far end swings up, and so on, or a grandfather clock that has a pendulum inside swinging back and forth to keep time. Before we get into the mathematics of how a pendulum works, I'd really like to show you a quick video, which is a little bit internet famous. It's a lecture performed by Dr. Walter Lewin at MIT in the States, and this was actually his last ever lecture, and he was super epic, physics university professor who performed the most awesome demonstrations live.
Now I want to return to the conservation of mechanical energy. I have here a pendulum. I have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. MGH is the work I have done, believe me. I've increased the potential energy of this object. 15 times 10 is about 150 joules. If I let it fall, then that will be converted to kinetic energy. If I would let it swing from 1 meter height, and you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, they're called a wrecker ball. They use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish a building. You just let it hit, and it breaks a building. And that's the whole idea of wrecking. So you are using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. See you Wednesday.
Just as you saw in the video, a simple pendulum consists of a mass hung from a string from a fixed support. The mass is commonly referred to as the pendulum bob, and when the bob is displaced from the center hanging, meaning that it's lifted up to the side like this and then released, it begins to swing back and forth. In this diagram here, the gravitational potential energy of the pendulum bob is at a maximum at points A and C, whereas the kinetic energy of the bob reaches a maximum at the lowest point of the swing, or point B. This conversion between gravitational potential energy and kinetic energy continues as the pendulum bob swings from side to side. Use the diagram of the 2 kilogram pendulum below to respond to the following questions. What is the gravitational potential energy of the pendulum bob at point A? Let's start by writing down the things that we know. The mass of the pendulum bob is 2.0 kilograms. G is 9.81 meters per second squared. Looking at the diagram, we can gather some more information. For example, the height of the pendulum above the ground at point A, or HA, is 0.75 meters. How high is the pendulum at the equilibrium position, or point B? Well, this question has some information that we actually don't need in it. We call this 1 meters a red herring, which just means that it's information we didn't need. All we care about is how high above the ground the pendulum is. So at point B, that's 0.5 meters. Question A asks us to find the GPE of the pendulum at point A. So we're looking for EP, which is a product of mg and the height at point A. Let's substitute in our numbers. EP is 14.7 joules. Part B asks us to find the speed of the pendulum bob as it passes through the equilibrium position at point B to the nearest tenth of a meter per second. In order to do this, we have to assume the pendulum was released from rest, which in physics terms means that the speed at point A, where the pendulum was released, must be zero. In this case, we're looking for the speed at the equilibrium position, or VB, the speed at the bottom of the swing. Please pause the video here while you try this question, using the same law of conservation of energy formula that we've used in the past. Except this time, we're comparing point A to point B on the swing of a pendulum instead of the track of a roller coaster. Okay, let's go over the solution together. We start by crossing off the kinetic energy at point A, given that the pendulum was released from rest, which means it wasn't moving. Then we substitute all the formulas for our kinetic and potential energies and use algebraic operations like multiplying each side of the equation by 2, dividing every term by m, and then subtracting 2GHB so that we get VB by itself. The final step is square rooting each side of the equation, and we find that VB, or the speed at the equilibrium position, is 2.2 meters per second. Okay, it's time for assignment 5. Please don't forget to check your solutions before turning in your work. Bye for now.